So A-PHY finally does give the industry that long-awaited standardized high-speed SerDes solution, offering extremely high bandwidths with very low latency and highly robust in the automotive electromagnetic environment. The ecosystem, you can actually see some examples of it here right behind me, is taking off extremely quickly. In only a year and a half since Valens started shipping our engineering samples of the world's first A-PHY compliant chipsets, we've seen take up in cameras, in radars, in LiDARs. We've seen test equipment vendors running to adopt this standard, SoC vendors. It's basically everywhere. The cabling and the connectors that need to support A-PHY are already there. So very, very quickly, yes, the ecosystem is emerging, and we are agnostic, for example, to the type of sensor. So as you can see behind me, it doesn't matter if it's cameras, it doesn't matter if it's radars or LiDARs. We can extend the traffic from those sensors at link speeds of up to 8 gigabits per second with packet error rates of 10 to the minus 19, which is orders of magnitude better than other technologies. So it's the right technology that the industry needs, and that's why we see the ecosystem emerging so quickly. As mentioned, very, very high bandwidths. A-PHY spec will take you up to 16 gigabits per second in its first version. With our first generation of A-PHY compliant chipsets, are supporting 8 gigabits per second in the downlink. We already have work underway for our next generation, which is 16 gig per second. EMC performance is critical. So the automotive environment is extremely harsh in terms of the electromagnetic noises that the systems are exposed to. And this is only going to get worse as more systems go in, and also with the move to electrification with higher and higher currents that cause more and more noises. So we are already showing test results from EMC testing at JASPAR in Japan, which is basically the umbrella organization of the entire Japanese automotive ecosystem. They've passed testing running our chips at 8 gigabits per second without any failures whatsoever. JASPAR already are on their website showing a reference design using these chipsets. But a secret sauce that we bring to the industry is also the ability to run up to 4 gigabits per second on a single unshielded twisted pair. No other technology is capable of doing such high bandwidth over such simple cabling, and that introduces real system cost savings for the OEMs. Today, radars are implementing edge processing. So inside the radar, you need to have a fairly big processing unit, an MCU, which takes the raw data from the radar chip, the MIMIC chip. It basically compresses it and then passes low bandwidth data down to the ECU. And the problem there is what's happening with that edge processing is that you're losing data. You're not getting all the raw data at the ECU. With Valens A-PHY compliant chipsets, the VA7000 family of chipsets, you can now implement a lean radar designed for more centralized processing. And this is what's on show here. This is a radar from a Korean company called SRS, and they've taken away the edge processing. What they tell us is that this is much, much smaller, around about a quarter of the size of their existing radar. It's also cheaper because there's no processor in it. That processor also would normally consume a lot of power, so this is a lower power solution, meaning that we can run the power over the same cable as the data. And in this case, because it is a 4 gigabit per second link, that's a single unshielded twisted pair, which again gives them cost benefits. So now we can have an array of these lean radars feeding raw data, uncompressed data down to the centralized processing unit. And that allows the vehicle, the radar system, to have a much better perception of what's going on around the vehicle. So it's raw data processing at a centralized location, leading to a much leaner, cheaper and more efficient radar implementation at the edge. For sure, EMC is really a challenge, and it's only getting worse. It's always been a very noisy electromagnetic environment, the car. I mean, you have spark plugs, ignition systems, you have window motors and wiper motors, and all of those are radiating electromagnetic noises. And so the challenge for the system is how to deal with that, and the challenge gets worse as the bandwidths increase, and this is the trend that we see in the industry, ever increasing link bandwidths. So we have brought a technology, I mean, it's specified and defined by the MIPI Alliance that is very, very robust. There are certain mechanisms implemented within the silicon, within the standard that we follow, that allow us to deal with the noises. And those include pulse amplitude modulation, which lowers the frequency on the cable to reduce the signal loss. But in addition to that, we have real-time adaptive noise cancelers that actually learn the noise that is attacking the system and are able to cancel it out in a very, very short period of time, less than a microsecond. And any data corruption is also handled by a physical air retransmission mechanism, which allows us to ask for the packets that were lost to be or damaged to be retransmitted, all at the physical layer. And all of that is done without influencing the overall bandwidth. We have a fixed latency of around about 6 microseconds that allows us to handle and do all of that magic to handle the noises without impacting the throughput or the delay of the data. And the overall result is a packet error rate of 10 to the minus 19, which, to put it into some kind of concept, is something like 1 error every 60 or 70,000 years. So it seems to be the way that the industry is going is to move the processing away from the edge and to have it centralized. And I think the innovation that will come with that, of course, is the goal of a software-defined vehicle, which, similar to our cell phone, will be a common piece of hardware that you can update and add to through software updates over the air. In order to do that, to have the processing centralized, you must have a lot of data flowing from the edge of the vehicle, the envelope of the vehicle, those sensor data flowing into that centralized processing. And that brings us back to the MIPI A-PHY standard, and of course our VA7000 chipset that provides that high bandwidth, low latency, extremely robust link to make that centralized processing and the software-defined vehicle of the future a reality. Truck visibility issues are well known in the trucking industry, and of course it's different from a passenger vehicle, because when I want to reverse, for example, I can look through my rear view mirror and I can see what's happening at the back of the vehicle. With trucks, of course, you have no rear visibility at all, and until this point in time there was no way to add a reversing camera to the back because you have a separate tractor and trailer, and those are joined by a power cable only. And the question is, how do you get a video signal from a camera at the back across the power line jumper cable from the trailer to the tractor? And this is where our first generation of chipset comes in. Our VA600R chipset actually allows the truck fleets to add rear view cameras and to send the video data across power lines, standard power line cables, standard power line connectors, up to a display in the cabin. That's a project we're doing in conjunction with Stone Ridge, who are a major tier 1 based out of Novi, Michigan. And we've demonstrated that technology widely, and there's no other technology that's capable of working over those power line connectors. But of course, our newer MIPI A-PHY chipsets are also suitable for the trucking industry, for example, for mirror replacement, for front cameras, and also for driver monitoring systems as well. So it doesn't matter if it's rear-facing cameras or if it's side cameras or front cameras, Valens can bring a technology to market that allows the OEMs and the tier 1s to implement those systems.